All right, so welcome back everyone, and welcome for the first time attendees today. Today we're talking about the process functional modeling. It's the continuation from the last session that we had about the system functional modeling, where process functional modeling is a higher level analysis of the entire process and combining that together with a system functional model when we're analyzing specific operations. In general, it's a way to understand our processes, understand our systems, learn how they work, understand what's the most problematic components again, and potentially even simulate the changes that we're planning or what we want to make, and see how they affect the entire process and the entire system, the entire outcome eventually. So today, Anatoly leading this webinar or masterclass. So the stage is yours, Anatoly.
Thank you. Can you
just one last note? If anybody has any questions, please leave comments. I mean, you're welcome to ask verbally, no problem. If it's something that can wait, then just leave a comment and we'll address all of them as we towards the end.
Okay, great. I want to start with our website, which is www.breezeguru. You can find a lot of information here about functional modeling. You just click search and write down process functional modeling, and you will find a lot of information about process functional modeling, maybe more than somewhere in the world. So let's go to the platform. You know, in order to get to the platform, you need to create account. I have an account, and I already prepare open project. I picked up the example from microelectronics, but please don't afraid. Microelectronics is no miracle in microelectronics. It's regular chemistry, primary school, and we will analyze the very first operation in microelectronics. We have wafers, silicon wafers, and we need to create silicon oxide layer on the surface of the wafer. How it is done? Wafers are loaded into the boat, and boat is loaded into the furnace, and in the atmosphere of oxygen and concentration of oxygen is managed with the additive of nitrogen. We oxidize at relatively not very high temperature, 300 or something like this, degrees centigrade. The problem, and this is a chronicle problem, is that bottom wafers always display a high thickness, which is not a problem, but they have high sigma, higher standard deviation, which is a real problem. It could be 2, even 3 times high. And equipment is built, this is tube, quartz tube, and heaters. Heater is built from number of sections that work independently and managed independently. Each one has its own thermocouple for management. So typical root cause for this, typical engineer says, this is the problem that related to flange. flange, this is what is gives us this problem with thermal conditions in the bottom of the furnace. And solutions, there are different solutions. For instance, to use dummy wafers, to use some these wafers for products where limits for standard deviations are much wider and very genius, but not not very good. Let's analyze it with a problem with the process functional modeling. By the way, we can click and ask AI to read our description, and it gives us 70%, and also, which is not so bad, and gives information what could be added here. So I will skip problem statement. Here we also have AIs. The problem is in the bottom part of the furnace, the thermal conditions are different. So we go directly to the tools. We have 11 creative thinking tools. And this tool, process functional modeling, is here. And you have here button, learn more, and you can learn how to operate with this tool. So everything is written very, very good. So let's open it. And description, I like pictures. I already picked the picture and just paste it here. This is a equipment. This is a furnace, as I told, that separated in different heaters, wafers, boat, parts tube, nothing special. But this is this process could be separated in different operations. For instance, first we should load the wafers into the boat. Let's give this operation name preload.
Почему не работают наушники?
I'm so sorry.
Опять.
Sorry, say it again. Yeah.
I muted.
Okay. Preloading. We need to place wafers into the boat, into the boat. Okay, the next operation, we should load the boat into the furnace. Let's say loading. The next operation, we need to furnace is always at elevated temperature, 300 degrees centigrade. We should wait for to stabilize the temperature. Stabilization. Get stable temperature. The next step, oxidation. We just give oxygen inside of the wafer. Oxygen interacts with silicon plus O2, and it gives silicon oxide primary school layer. And the tips, when the interaction is completed, we should unload. Unloading the boat. And after that, the 6, we need to cooling the wafers and the boat, and unloading the wafers and unloading the wafers. And when we unloaded wafers, we need to measure thickness. It's a silicon oxide thickness, measurement. Okay, great. Let's go to the model, and let's create process flow. Add step, and I will give a name. We said the first one will be preloading. Loading wafers loaded to the boat. Okay, save. The next operation, ask your questions if you need it. The next operation, we said it's loading. Loading, we need to load the boat with wafers into the furnace. I love to write because when you're writing, you're thinking. Yeah. The next step, we said stabilization. Stabilization. Get a stable temperature. Okay. And after that, oxidation. Oxidation. Oh, oxidation. Oh, oxidation. It's an interaction of silicon wafer with oxygen. Great. And after that, when the process completed, we need to remove it. We need to unloading the boat from the furnace. And the next one, we need to cooling and unloading wafers from the boat. Okay, and the last one actually, it's measurement silicon oxide thickness measurement. Save. So we don't need this. We can click disable heading. Or if we need to add something, we can click enable heading. Very, very useful. So the next, we already built the flow, but empty flow. First, we should define what type of operation. each one. There are 4 types of operation. There is productive operation. It's irreversible changes, like drill hole in the piece of in the plate of metal, providing its temporary changes. For instance, mark the place where the hole should be drilled, temporary changes. Corrective, it's typically removal defects, because our productive or providing operations are not ideal. We need corrective operations. It's like remove bars after drilling, or metrology. Metrology, just parameter management, measurement. So preload, it's of course it's not irreversible. It's temporary change. We can mark it as a temporary change. Loading, I would say it's also providing stabilization. It's also temporary change. It's also providing oxidation. When we created silicon oxide on the surface, it's also already irreversible. We can remove it, but it's actually irreversible. It's productive operation. Unloading is also providing, or maybe corrective, doesn't matter. Cooling, it could be corrective. And no, I would say stabilization is a. Oh, I'm sorry. I'm so sorry. I would say this stabilization. What's happening? Stabilization is a corrective, and measurement is metrology. So the next step, we should create functional model for each operation. For instance, let's go inside of this operation. We can write down what's happened during preloading. We can write that furnace is open. Okay. Heaters keep temperature 300 degrees Celsius. What's happened? What's happened? Atmosphere. Atmosphere. And to flow. What else? Boat is empty, and wafers are in the it calls full. This is a plastic box to keep and transfer wafers. So we need to pick up wafers and place it. We need to pick up wafers and place them to the boat. Clear, yeah. Everything is clear. Let's create a functional model. So product target, we need to move wafers. It means our product is wafers. And we don't have super system. We have component both. Nope, both. We have both keeps wafers. Yeah. Keeps wafers. We have FOP. This is box for wafers. Also keeps wafers. Keeps wafers. We have here. Let's take here, which we have wafers. Wafers keep here. Nothing to do. Yeah. Keep here. Let me make some. We have what do we have? We have robot. Robot. Oh, I'm so sorry. We have robot, which moves wafers. Moves wafers. It takes from FOUP and places to the board. We have N2 gas, which moves here. It should remove here, but it's okay. Moves, but insufficiently. Let me move it. And N2 gas is also heats both because it's hot gas and it's heats both, and this is not what we need. And we have heaters. They heat gas. They heat gas. They heat. We have furnace. It's like game, you know. I love it. My students also like it very much. It heats furnace, and furnace heats wafers. And also this gas is coming from the outside, and it comes cold, and it cools furnace, and it's not so good. And we have thermocouples. We have thermal. Well, I will write like this: thermocouples. They are heaters in form, and furnace heats thermocouples. And we have controller, temperature controller. Which directs heaters. Directs heaters, and Thermocouples informs also inform a controller. We can continue, and let's have a look on the ranking. You're already familiar with this. We have recommendations here. You can click to the recommendations and try to improve the different components, different functions. I just want to say, if we continue this, we will have no enough time for this. Therefore, I made it, and I just want to show you the result. Which one? This one. Yeah.
Probably the second one. Yeah.
The second one. Yeah.
Mm-hmm.
So this is the explanation. This is the flow, and for each operation, why it makes sense, because for each operation there is different product and different components, and for each one we can have a look on the ranking, and we can improve it. And let's go to the flow. This one, oxidation. I described what's happened during this operation, this stage of operation, this step of operation, and I created model. You see in the oxidation, it's a silicon oxide layer. And here we can have a look, but let's have a look on all on the whole process. This is a operational merit. This is a ratio of functional and problematic rank. And if it's if it's above 2, it's green. If it's below 2, it's red. You see what's interesting? These two, loading and unloading, are red. What does it? And if we go to the summary, in the summary you also see that these two steps in the two operations are red. They are problematic. What it gives us, makes us think. Don't think about flange. Don't think about flow. Think how loading and unloading could create high standard deviation. First of all, what's happened in loading or unloading? We all understand it. These two operations where wafers move, and all the rest of the steps, wafers are not moved. I'm not talking about preloading. They move within the furnace. Okay, what's happened? Can we create a model? What's happened? We created model very, very easy. When we insert both with cold wafer, actually we insert wafers at room temperature into the furnace, which is at 300 degrees centigrade. And just try to imagine the first cold wafer came to the first thermocouple, and it says to thermocouple, it's cold. Please add temperature. Instead of to wait and get real feedback, another cold wafer came to this thermocouple, and so on, so on. And what's happened? that when we loaded our boat with cold wafers, we gave wrong information to the first thermocouple. Therefore, bottom part of the wafers are overheated. And this is what we found out. How to solve this problem? Who can say? Very easy. Just to disconnect feedback in the thermocouple, at least in the first thermocouple, from the heater, from the controller during loading and unloading. Okay, so people said, so trivial solution. Why do we need a platform for this? And I always say, guys, you spend year, even more than year, to try to explain, to change something in the flange, and you did not solve it. Here, you made very, very not easy work, but you solved this problem. What else we can find from functional modeling? Here is productive operation effectiveness. Again, this is a ratio of how harmful and how functional our flow. This is a breakdown of different types of operations. By the way, what I found that typically in microelectronics, productive operations never exceed 20%, typically lower than 20%. Now, there is a general recommendation. We all know it, we just don't remember it, that productive operation is the only operation that increases value of the product. All the rest of operations, like providing corrective metrology, just wasting time and money. Therefore, we can create a strategy, and our system gives us tips. For instance, oxidation is a productive operation, so consider improving. Providing operation, we should not think how to improve providing operation. It doesn't make any sense. But we don't need to improve the process, how we mark the place where we need to drill a hole, for instance. No, we should improve the process of drilling. We should improve the process of oxidation and not not providing. By the way, from this point of view, to investment into the lithography is, as to me, it's a wrong way. This is really wrong way. It's good for companies who produce equipment for photolithography, but now we should think how to deposit and remove locally, and not to spend money on the providing operation. Now, regarding corrective operation, our system recommends do nothing with corrective operations. Again, don't improve it. Don't spend time and money. When you improve, when you improve productive operation, when you eliminate or make it easier, make it shorter, providing operation, this corrective operation will disappear. Regarding metrology, it's good to measure something. The question is, we always should ask question, do we need this information? What will we, how do we use this information? Will it will increase value somehow, value of the product based on this information or not? If not, don't do it. Don't measure, don't spend time. Now, let's have a look, oxidation, productive operation. Let's have a look on what can we do with oxidation. Let's have a look on the functional model again. I would say this is good, but I would say based on this analysis, of course, I spent more than 40 minutes for this. Oh, what I would say all this process looks trivial, but it's paradoxical process. What I mean, we have in the beginning wafer with air. What air is a mainly mixture of nitrogen and oxygen, and some insufficient additives which are not affecting oxidation process. What we do, we remove air with nitrogen that we purchased and brought in the cylinders. And what else? Remove it again with oxygen. Do you think it's makes any sense? Wasn't it? You know, when we pay for nitrogen, we pay for the quality of nitrogen, and quality of nitrogen, it means this nitrogen is very, very, has very low contamination with oxygen, no oxygen. And we pay a lot of money for this. On the other side, we buy oxygen, and the cost of oxygen, the price that we pay is that this oxygen doesn't contain nitrogen. What we do on the next step, we mix it. I'm so sorry, guys. I see there is a lot of possibilities to improve and make this process easier, cheaper, and effective, less problematic. And of course, we can clone this version and start to think how we use air, which is excellent component for oxidation. Guys, I want to say this is trivial, but this process exists everywhere in each fab where microchip chips are produced. We are very good engineers, but we have to take into account that our brain is biased by our previous experience. This is what moves us always to the history backward instead of move us forward. We should think forward. We should so-called think out of the box. And in order to make it, we should use creative thinking tools. No other way. Only to use creative thinking tools. I'm sure Alex can add something. about
Yeah.
this.
No, so
Yes,
the
please.
one thing that I wanted to add, can you go back to the process functional model, to the process flow? So what we see here, so Anatoly built all of these steps and modeled each and every one of these operations. And basically what we've got is a ranking of the current state of the system, right? Now, when we're trying to understand how we should improve the system, should we improve the entire process, instead of usually what happens, people go into the room, brainstorm ideas, and they say, okay, great, let's try this. They try this, it's not working very well. They already wasted money. They already invested a huge amount of money, especially if it's microelectronics industry, it's very expensive. And then something didn't work the way they expect, and then they're trying again and again. So it's this iterative, endless process of trial and error, which at some point may or may not yield any results. But at the end of the day, this particular project will run out of money and people will just stop, or the organization will stop investing in this. They will say, okay, it's good enough. But think about it this way. Since we can model each and every one of these changes in every one of these operations, we can pretty much simulate how effective that change, how much gain we getting from particular change without investing a single dime into implementing them, right? I don't know, Anatoly, if you have one of these operations with few versions of functional models.
Oh, here you mean?
Yeah. Yeah.
No,
But
it's just
no, that's fine. But let's say like Anatoly proposed in this oxidation process, let's remove nitrogen, but let's remove oxygen and just use the air, right? So the entire model will change. The entire ranking will change for this particular operation. And without implementing, if you go and switch to version 2.
Mhm. I'm sorry.
No, you already have the version 2.
Yeah. This is what I wanted to say. The only thing what we need is this function. We need to create the oxidized silicon, create silicon here. And all these components we don't need. We don't need. We have this one. We should
Right.
think how to reduce, how to make it easy, smaller, and less expensive. Each component costs money.
Right.
Yeah.
Let's, just for the sake of an example, try to remove one of the components, regardless if it's right or wrong. But at the end of the day, we changing the model. We proposing a change and we saying, this is how we're planning to change it, right? Now, if you go to the ranks, now you have two different versions of them with its own ranking. So you see that in this particular case, the rank of operational effectiveness and operational perfectness actually went down. So that's an indication whatever change we're trying to do, it's not going to be a very good change, right? So why even invest in that before into implementing, into validating, and all of that? It's already proof enough that whatever idea for changing this operation, don't pursue it. Look for something else, right? And by doing this, you will have much faster iteration of these proposed changes, very, very cheap, very quick. And that's,
Right.
I think, that's in my mind the biggest benefit of these functional modeling and process functional modeling as a one big tool, how you can improve the entire process, make it cheaper, make it more reliable, solve problems that each and every operation causes, and so on.
Yeah, great. Thank you.
There is a question from Sergio. I can see the causes, the cause investigation of the lower wafer thicker. Saving, that's kind of a investigation done with other tools. So yeah, in Sergio, in here we focus specifically on the functional modeling, right? Something that we didn't show here, obviously, is of course we need to find the root cause. Once we know which operation to focus on, and we model the components, we potentially already have a component to blame in mind, if you will. I don't know if that's the right term to say, but let's say we identified, hey, a specific component is most likely to cause a problem. Now, the next step would be to go into root cause analysis of any kind, whether it's 5 whys, cause and effect chain, and so on, and trying to understand how this particular problem can be caused by that particular component or an operation, right? So yes, this is at a high level. Process functional model is not an analytical tool for root cause analysis. There are other tools for that. This is a tool to understand first of all, understand our system, understand our processes. What's the most what operation is the most contributing the most to the product, or potentially causing the most problems, right? Once you have that information in place and you understand how physically that symptom is caused by an operation or a component, now you can propose changes. And proposing these changes, it goes back to the model, and we say, okay, we decided to change it this way. Does it actually provide the value that we expect?
Yeah, right. I want to say, yeah, root cause analysis with the cause and effect chain of 5 whys, very, very strong tool. But again, it's not easy. If you do it as necessary, it's not easy. Like functional modeling, like process functional modeling is not easy. Each tool is not easy. But you have to make a choice between not easy or impossible. Because when people are sitting in the conference room drinking coffee and say, oh, let's change the nitrogen flow, it's guessing. It's like, like to say 5 red. This is the same. It has no engineering sense. It looks like engineering solution, but it's not. It's not. If it come out of root cause analysis, it come out from modeling, it does make sense. What I recommend, guys, try. But one more point: don't write down test. Don't test the software. Software is okay. Test it thousands of times. Test your skill in the usage of the tool. The more you use tool, the more effective you solve your problems and generate innovative ideas.
Yeah. What we've
maybe
yeah,
it was it was misleading at the very start of this presentation when I read that the problem was the thickness, the different thickness, and the variability of that. And also in the past, not so sorry, I have my dogs that I think that are eating
That's all good.
someone, but okay. I used the process analysis, the functional process analysis, on a chemical a chemical reaction in order to transform the chemical formula in a process and we use that just to improve the cause effect analysis and to see where we could act in order to change the bad behavior of that process. So we use not as a industrial process, but a chemical process described as a process, just like an industrial one.
Maybe you can share with us your result if it's
No.
possible. No. Okay. Okay.
Yeah, Sergio, it makes total sense. Again, process doesn't have to be on any specific level. It depends on the scope that you're trying to analyze, right? If you take, for example, Intel manufacturing processes, right, or any microchip manufacturing process, you're talking about months and months of process, which consist of a lot of other processes underneath it, and so on. So each and every one of these can be viewed as a separate scope for analysis. And there is nothing wrong with it, right? It could be a very small, a 5 minutes process, as well as the entire thing. And of course, if you're focusing on a smaller scope, it's easier to analyze.
Yeah,
because
sure,
there's
you
less
can.
things to think about.
Yeah, you can analyze diffusion, absorption, specific absorption, interaction, and oh yeah, great, very, very good what you said. Yeah, to separate all this and formation of oxide, and if it's too small, it can disappear. It should be able to interact with some other silicon oxide molecules. It's in the level of molecules to create phase. Yeah, it's very, very, very interesting flow we can analyze.
Yeah.
Yeah, when I teach functional analysis, I generally say that a functional analysis is a picture, but nothing is a picture because time exists. So everything is a process. If you can synthesize it in a single shot, in a single picture, okay, but is a limitation. Everything is a process that can last few milliseconds or years, but everything is a process.
Exactly.
Right.
Exactly. You're absolutely correct here. And back to the scope, if you think about it, and that applies to all tools out there, no exception. Let's say even root cause analysis, right? You can go to the level of, to the molecular level of why and what happens behind the scenes, right? No problem. But do you need to? Right? Maybe it's enough to stay on the components of your system level. Maybe it's enough to go to the electrical level. Maybe it's enough to go to the management level. Nobody knows, right? It depends on what problem that you're addressing and what is it you're trying to analyze. So the context is very, very important in any problem-solving process.
Yeah, great. Thank you.
I'll pause the recording for now.